All right. So welcome, week 9 out of 10 here. So we have 4 class meetings left, and that's it. Then we're done with the course, except for the exam. So this is coming up quickly. My plan is to talk a little bit about state machine synthesis today with respect to the homework that I've graded and turned back to you. To talk about any questions on Lab 6, and then to continue talking about Verilog and working with the Model Sim software for that. And heads up, so I finished grading the 250 Homework 5 last night, and I left a recorded media file with my comments in it, and then somebody wrote me this morning and let me know that the file was completely blank, empty silence inside, and something glitched out when I recorded those last night, so I've re-recorded those and reposted them. So if you tried to listen to my comments yesterday and there was nothing there, I've reposted them, so you can go back and give a listen again. So hopefully that's working this time. All right. So any questions before we get started? All right. Well, let's talk. Let's talk about the homework that I've graded and given back to you. Um, so I graded question 5. All right, and let's pull this up from the assignment. So question 5 was this mood predicting machine, right? It's got 4 states: reset, happy, sad, and so-so. Um, and this key tells us how to read this table. The name of the state is inside the oval, and then there's an input slash output. The input is called X, the output is Z. And so we have 4 states, okay, and we're asked to use JK flip-flops to build a machine, a circuit, that performs this set of state transitions. So one of the first things you have to do is decide how many flip-flops do you want. And, most people chose 2 flip-flops. That's sufficient. And let's call our flip-flops something like Q1, Q0. Okay, and let's list these 4 states. So reset, happy, sad, and so-so. And you have to choose how you're going to use your flip-flops to represent those states. So you make a state assignment table. And most people did this. And it really doesn't matter how you assign these states to the flip-flop values. You'll come up with a different circuit depending on this assignment, but your circuit in the end should do the same thing, which is realize this set of state transitions. Okay, so that's the first piece, is come up with a state assignment table, and then make your state transition table. So there's a single input here called X. Okay, and there's a single output called Z. So X is to the left of the slash, Z is to the right. And so we're going to make a table, and you can do this a variety of ways, but let me just show X as our input, and then our present state. And our present state is Q1, Q0. And so we have 8 rows in our truth table. Right, because there's 4 possible states, and for each of those there's 2 possible values of that single input X. And we can fill in the output. So X is an input. Q1, Q0 is our present state. We can fill in the output from this table. So the output, for example, if you're in state 0 and your input is 1, your output is 0. So state 0, input 1, your output is 0. But if you're in state 0 and your input is 0, your output should be 1. So your output becomes 1 right here. And so you want to very carefully fill in your table using this set of combinations of present state and input. State 0, 1, input 1, output is a 0. State 0, 1, input is a 0, output is 1. So state 0, 1, input 0, output is 1. State 1, 0, input 0, output is 1. So 1, 0, input is 0, output is 1. And then state 1, 0, input is 1, your output is again 1. So 1, 0, input 1, output is 1. And then state 1, 1, which is our so-so state, input of 0, output is 1. And input of 1, our output was a 0. So unless I made some mistake in here, and it's easy to make mistakes, right? This is what the output column looks like. So that's one piece of your state transition table. The other piece is your next state, which we can think of Q1 plus and Q0 plus. And this again comes from the table. So I've got a sloppily drawn version of the state table here. If you're in state 0, 0 and your input is 0, you go to 0, 1. 0, 0, input is 0, go to state 0, 1. If you're in 0, 1 and your input is 0, you go to 1, 0. So 0, 1, input 0, go to 1, 0. If you're in state 1, 0 and your input is 0, you stay at state 1, 0. And if you're in state 1, 1, your input is 0, you go back to 0, 0. So this is just transcribing from the circuit diagram to your state transition table. And then we have the last 4 rows where the input is a 1. So if we're in state 0, 0, input is 1, we stay in 0, 0. If we're in state 0, 1 and the input is 1, we stay in 0, 1. And then if we're in 1, 0 and the input is 1, we go to state 1, 1. And if we're in state 1, 1 and the input is 1, we go back to 1, 0, and that's the only sort of backwards direction. Okay, this is nothing more than, enumerating all the possible states and input combinations, and then filling in the output and the next state from the table, from the state diagram. Okay, once you've done that, right, you're done with this diagram for now. And so now comes the question of, based on the types of inputs that we have, the types of flip-flops that we're using, how do we want to set up these inputs and outputs? Hold on, I'm playing with my chat settings here. All right. So we're using JK flip-flops. So we need to describe the JK inputs for flip-flop 1 to go from Q1 to Q1 plus. So let's just look at the current value of Q1, the next value of Q1, and what we want J1 and K1 to be equal to. And there's a very straightforward way to fill in J1 and K1, which is just to look at the new value. Because we know with a JK flip-flop, right? If we put J and K both to 0, Q doesn't change value. If we put J and K both to 1, Q toggles. If we set JK to 0, 1, the flip-flop goes to a 0, 1, 0 goes to a 1. So if we want the new value of the flip-flop to be 0, we can just say, hey, set our JK to 0, 1. If we want our new JK to be, our new flip-flop value to be a 1, we can say, hey, set JK to 1, 0. And we can do that. Okay? That will work, but it's not terribly efficient. Because remember, when we have JK flip-flops, we have this notion that if we want to change from a 0 to a 0, yeah, we could say 0, 1, but we could also say 0, 0. Right? Because a 0, 0 on J and K says don't change the flip-flop. And since the flip-flop's already at a 0, if we set JK to 0, 0, it'll stay at a 0. If we set JK to 0, 1, it will say force the output to 0. In both cases, the output is 0. So you'll see this flip-flop excitation table, which says for a JK flip-flop, if this is the current value and this is the next value you want, here's what you should set J and K to. So if we're going from a 0 to a 0, we can actually set JK to 0 and don't care. If we're going from 0 to 1, we can set JK to a 1 and a don't care, and so on. So you fill in the inputs for J1, K1, you fill in the inputs for J0, K0, and then you have to write equations. Z equals, J1 equals, K1 equals, J0 equals, K0 equals. And how do you do that? Well, you can do a straight sum of products, but since you have don't cares, and you're going to have 4 don't cares in every column, you can take advantage of those in K-maps, because a K-map, you're allowed to cover a dash, you're not required to. So you use the dashes where it helps you get larger rectangles or fewer rectangles, and you ignore them otherwise. And hold on a second. Alright, so let me pause a second because I've got an email from a student who is having trouble getting into Zoom. Nope, looks like they have gotten in. Okay. Alright, so you write your equations and then you sketch a circuit. Okay. So most people seem to have the right idea with this problem. Most people did this state assignment table. Most people came up with, you know, something pretty close to this. A lot of people did this JK where they just said 0, 1 or 1, 0 to clear or set the flip-flop. And like I say, that works, but it's going to be more efficient to take into account these don't cares. Okay, so you want to do that when you can. And then you want to sketch a circuit. Okay, so I was feeling really good about this homework until I got through all of the grading and I started going back and reflecting. So I saw some things in here that are a little worrisome. First of all, when you look at this problem, right, there's always a key to go with these state tables, these state diagrams, which is showing you the thing inside the oval is the name of the state. And then on the transition arrow, you'll see something called X, followed by a slash, followed by something called Z. So right here, the name of this state is sad, and if X is 0, then Z is 1, and we transition back to the sad state. Okay, that's how we interpret this. And when you see a key like this, right, the thing before the slash is the input or inputs, and the thing after the slash is the output or outputs. Okay, so if you had 2 inputs, you'd see X1, X2, or X1, X0, or whatever the person decided to use. So about a quarter of the circuits that I saw for this and the analysis that I saw for this called their input A, and they called their flip-flops X and Y. And that's very confusing, okay, because the input is supposed to be X, and if you use X for the name of a flip-flop, then, you know, somebody reading this is going to think that that X is the input value, and it's being used as a flip-flop output, and it's just going to be all kinds of mismatch with what you're trying to do here. So that was one thing. Pretty much every time that I have done this in class, I have called my flip-flops Q1, Q0. The book will call them Y1, Y0, or sometimes Y2, Y1, or maybe Q2, Q1. Okay, I try to be totally consistent and always call them Q1, Q0. Okay, or Q2, Q1, Q0 if there's 3 flip-flops. But a bunch of people call their flip-flops X and Y. And I'm not sure where that came from, but these things really, they go together as pairs. It kind of makes more sense to think of them as you know, Y1, Y0, or Y2, Y1, or something like that, instead of just X and Y, particularly when X is one of your inputs and then Z is the name of your output. So that was a little unusual. In the K-maps for you know, finding the J and K inputs, There was a case where, you know, something turned out to be, and I don't remember what the specifics were, but it was something like, you know, xq1 or x bar q1 bar. Okay, and if you take an equation like this and you make a k-map, you get a checkerboard. Okay, and if you go back and you think about exclusive ORs, this is actually equal to xq1, sorry, to x ORed with q1 with a bar on top. Okay, that is logically equivalent. And so if you want to build this circuit, you make an XOR gate with an inverter on the end, and X would go into one of the inputs and Q1 would go into one of the inputs. And in all of the homework assignments that had this in the circuit, there was no mention of an XOR anywhere in their work. Right? It went directly from, you know, a truth table or an expression like this into an exclusive NOR gate. That's a step that you want to show. Okay. If you're doing this for your own purposes, you don't have to show all your work. But for homework, you always want to show your work, particularly when you're doing sum of product, K-map, sum of product, minimize sum of product, another sum of product, and then bang, an exclusive NOR gate suddenly appears in your circuit, right? You want to at least show the step where you said, you know, my input is equal to this, which is also equal to an exclusive NOR, right? So that's an important piece. All right, K-maps. So let's say this is your K-map that you're coming up with. A number of people did the following. They made a K-map with like Q1, Q0, and X. I'm doing this backwards. So let's do X and Q1, Q0. Right? But they made a single K-map for, say, two variables, like J1, K1. And then they filled in from their state transition table, you know, 0 dash and 1 dash and 1 0 and 0 1 and 0 1 0 1 1 0 1 0. And I've never seen that before. I've never seen a K-map where we had two separate variables inside a single K-map. I've definitely never done that in class. I've never talked about that, and I don't even know exactly how to interpret that, because how do you cover your ones in this kind of K-map? Well, if you're really good at covering ones in your head, right, I can see that, you know, I would cover this one like this, and this one I could cover with this, right, and do something with that, right? And then to cover my second ones, you know, I could cover these two together, and I could cover this one with a don't care. But there's no real way to show that. But yet people did that, and they came up with the right equations. And so there's some missing steps in there. And certainly if you do this and you come up with the wrong equations, there's very little partial credit available, right? Because this is not how you do a K-map, right? So it's a lot of writing, I understand that, but one K-map per variable, okay? Make a K-map for J1, make a K-map for K1, J0, K0, Z, 5 K-maps. Okay, and then you can very clearly show, you know, how you're going to cover the ones and optionally cover the dashes. And yeah, I mean, like I say, you know, somebody here's saying that they were lazy. Yeah, I mean, this is a ridiculously long homework assignment, right? And I warned you about that. It's the longest homework assignment of the whole course. And you know, 15-20 pages, pretty typical, right? But on the other end of it, right, hopefully there's a really solid understanding of state machine synthesis, and that's what I feel I'm seeing from most people's homework, is like, yeah, you did this until you were sick of it and you burned through pencils and paper, but it feels like people understand how to do this now, okay? So I just want to make sure that if you're doing this on a test or something like that, make sure you go back to the good habits that you had earlier, right? Where you have, you know, one K-map for each variable, and you show all of your equation derivations and so on and so forth. All right. Couple of other things. A bunch of people, after building this table and then writing the equations for J1, K1, J0, K0, and Z, also wrote equations for Q1 plus equals and Q0 plus equals, and made K-maps and simplified them and came up with equations. And those might be interesting, but they're not really useful for designing a state machine, right? Why? Because these things are the future states of the flip-flops, right? And we can't really define what the future state of a flip-flop is by saying we want the future state to be, you know, X ANDed with Q0 ORed with Q1. The only way we can control the future state of a flip-flop is by setting its J and K inputs, or its T input, or its D input, depending on the type of the flip-flop. So the whole point of the exercise, why we're coming up with equations for the J and K inputs, is because those will let us control what the new value of the flip-flop is, right, according to the flip-flop's function table. So if we want the flip-flop to become a 1, if we want Q plus to be a 1, we can set JK to 1, 0. That sets the flip-flop to a 1. If we know the current state of the flip-flop, we can set it to something like this, right? If the flip-flop's currently a 0 and we want it to be a 1, we could set JK to 1 and a don't care, right? But ultimately, somehow, we're saying what should we set the inputs of this flip-flop to in order to make this the new value of Q1. So writing the equations for Q1 doesn't really give us something we can use in the design of our circuit. Okay, hopefully that makes some sense. All right, and then the last comment is drawing our circuits. So suppose we end up with, and I'm just going to make up arbitrary equations here. Suppose we end up with something like J1 equals Q1 Q0 bar, K1 equals Q1, J0 equals XQ1 or Q0 bar, K0 equals X bar, Q1 bar, and Z equals XQ1, Q0. Totally made up equations, okay? And we want to sketch a circuit. So we know how to sketch circuits with inputs, right, where we run the inputs vertically and we invert them and we have our outputs and so on and so forth. We can do the same kind of thing with our flip-flops. So for example, I could have my flip-flop over here, and here's J1 and K1, and here's Q1 and Q1 bar, and here's another flip-flop, J0, K0, Q0, Q0 bar. Everybody connected their clocks together. That is awesome. That's something that a lot of people get tangled up on usually in this course. Everybody seems to be treating the clocks perfectly right, which is great, right? The clock is just an input, goes to the clock input of each flip-flop. It doesn't show up in your state transition table. It doesn't show up in your equations for J and K. It's just the thing underneath. It's the heartbeat that's driving the whole system, right? It's kind of its own thing. And everybody seemed to get that concept, so that's awesome. So I can take Q0 and Q0 bar and Q1 bar and Q1, and I can do kind of what I was doing when I designed circuits in the beginning of the course, or in 120, right? I can run these Qs, the inputs of these equations, I can run those vertically, and here's my input X, and I can bring that down here, and I can branch off through an inverter. And so here's X bar, X, Q1, Q1 bar, Q0, Q0 bar. And now I just start building these circuits. So I want to take X, and I want to AND it with Q1, and I want to AND that with Q0. And there's my output Z. And K0 is supposed to be X bar ANDed with Q1. So I'll take X bar and I'll take Q1 and I'll AND those together. And that's going to be my K0 input. So I'll run this and come over to K0. And so on, right? So J0 is X ANDed with Q1. ORed with Q0 bar, so Q0 bar is right here. So that goes into an OR gate along with this. And that gives my J0. So I'll take that and run it back over here. And you do the same for J1 and for K1. And when you're done, what you really have is something you can put in a box. Think about a system diagram. This whole thing looks like this. There's an X going in. There's a clock going in. There's a Z coming out. Right? That's our machine for this system. This thing that predicts mood based on X, right? So your circuit diagram should reflect this. It should have an input. It should have a clock. It should have an output. And again, it's a lot of questions. It's a lot of writing for each questions. But in a number of the assignments, what people wrote was something like this: J1, K1, Q1, Q1 bar, and then they might have an AND gate over here, which says Q1, Q0 bar. And then K is supposed to be Q1, so they might have this labeled Q1. And I understand the spirit of that, okay, but that's not really a valid circuit diagram, okay? You really need to say, well, this is Q1, this has to go over here, and this Q1 has to come over here, and over here where you have Q0 bar, that has to come over here. And you want something that looks like this, something where you have an input and an output. And if you need an X bar, you take your X and you run it through an inverter, and then you use the output of that, and so on. And the disturbing part was the people who did this all kind of turned in exactly the same circuit. And it wasn't the circuit that corresponded to this diagram, and it wasn't a circuit that was correct, and it wasn't a circuit that was drawn in any way that we've ever drawn a circuit in this course. So I'm not sure what was going on, where that was coming from, if it was something the book does somewhere, or what. But anyway, let me know if you have confusions about why this is not what you want and why this is what you want, right? Something like this. All right. So that was question 5. That was the one that I looked at in detail. I glanced over, some of the other questions to see what people were doing. And again, it looks like people are on the right track. As long as it takes to do these problems, it takes almost as long to grade them. Okay, because grading is basically reverse engineering, right? How you got to this, and so it's that's one reason I pick and choose one problem that I think is representative. But if you're unsure about any of the other questions, right, you are very welcome to catch me in office hours and say, hey, can we go over this question, or can you look at this question and tell me if I did it right? And I'm very happy to do that, okay, because these are all really good practice problems. And you'll almost certainly see a state machine design question on the final exam. So it's definitely something worth knowing how to do and being confident in. All right. Also worth mentioning, I've had some people who have asked me, they're not feeling totally confident about state machines, and they're wondering, is this going to be a problem when they go on to 270 in the summer? Is this going to be a problem with the computer science sequence and so on and so forth. You don't do state machines in 270 for the most part. I mean, you never do this kind of thing, right? There's nothing in 270 where we're going to take this and we're going to make a state transition table. I don't think we ever deal with flip-flops in engineering 270. But those things, understanding those things is part of understanding 270. Okay? You'll be writing code in 270 where you'll be creating a software version of a state machine, basically. And we won't be talking about, J1, K2, Q0 bar, all that kind of stuff. But the type of thought process that goes into, analyzing or designing a state machine in 250 will be similar to what you're doing in engineering 270. And if you're in the CS sequence, right, we're doing CSE 223 right now in spring, we're basically designing state machines in software. Right? We're writing Java code that is implementing things that are stateful. And we're not talking flip-flops, we're not talking JKs, but people are revisiting the thought processes that they were using when they were taking Engineering 250. Right? At some level, they're doing something similar. So you'll see this stuff again in different forms. Okay? But if it's not, totally sunk in, completely rock solid, I absolutely understand this stuff, you're exactly in the norm, okay? It takes a long time for the stuff to really settle in and make perfect sense. And that just comes from doing it repeatedly, over and over. And if you're not an electrical engineer and you don't do this on a regular basis, right, that's not going to happen quickly. So don't ignore this stuff. I'm not saying it's unimportant, but don't be too concerned if you're coming out of it and you kind of got the idea but you're not totally 100% sure. That's probably about where you want to be, right? That's probably pretty typical. And you'll encounter it again, and it's like KVL, KCL, it's like calculus, right? It's a building block. It helps us scaffold other things on top of this. And as we do that, our understanding of this stuff will get stronger also. All right, so questions on any or all of this? And we won't really deal with stuff when we're talking about Verilog. We'll really be looking at these things from a different perspective. All right. So how is Verilog looking? So hopefully people have downloaded and installed and are running the LDEC HDL tool, which you need to use for your homework. And I haven't heard any comments or requests for help from anybody in this class on that, so I'm optimistically assuming people have downloaded it and are running with it, because at this point, if you're on a system where it doesn't work, it's probably going to be pretty hard to find a different option. So hopefully everybody took care of this last week, or haven't used it yet in the case of some. So I did find a quick start guide that I had written a few years ago for this. I have not gone through it and compared it to what exactly might be new in this particular version, so I haven't posted that yet. but I'll try to run through it and make sure everything is still making sense, and I'll go ahead and post that on Canvas just as kind of a written version of what we were doing last week, because that was kind of quick. But let's go through the steps again of making a project, right, a workspace, and writing some Verilog code and simulating it, okay? And then we'll dig more into Verilog itself and look at what we can do with that language. So, you know, you have to download and install the software. So I'm running the software right now. It's AVHDL. I'm going to start off by saying File, New, Workspace. Okay. Every project that you do, every circuit that you design goes in its own workspace. Okay, because these workspaces, they get big. Let me see if I can find the one that I was using. Right, so I was making a design last week called Summer 3, and it's got all of this stuff in there, right? So all of these files, and then there's a Summer 3 directory, and there's a source directory, which would have my Verilog code, and compile and log, right? So it's a few dozen files, and for bigger projects, right, this gets more involved. And if you have two different designs, both called, you know, the same thing in the same workspace, these files get mixed up with each other. And it becomes, you know, a red herring. You're trying to figure out what's wrong with your design, and there's nothing wrong with your design. It's just that the software tool is getting confused and compiling an old design that you had instead of your new design that you're working on. So I tell people a new workspace. And, you know, pick a reasonable location for it. So what should we call this? Let's call this Tuesday. All right. I'm going to say create an empty design. I find it really hard to reuse part of one design in another. If you want to do that, I would say just create an empty design and then just copy and paste the Verilog code, just using plain old copy and paste. Mostly we're taking defaults, but under the page where it asks for the default HDL language, change that to Verilog. Okay. If you look in the textbook for this course, there's one chapter on Verilog, one chapter on VHDL. Very, very different languages. Okay, trying to do the same thing, but the syntax is completely different. In particular, VHDL was designed by government committee. Okay, so it's very structured, but not necessarily as user-friendly or as intuitive in some ways as Verilog. But it's personal choice for some people. We're using Verilog. So make sure you change the default language to that. And then design name. I always make the design name the same as the workspace name. Just so I don't have to think too much. Alright, so then you get this nice empty window over here, and we can say File, New, and we're going to say New Verilog Source. Okay. And all of these options, right, these are different things we can do. System C lets us write C-like code to generate hardware. We can do a VHDL source and so on. We're going to do Verilog source. And that's going to bring up our wizard. Okay. So our wizard lets us design a system diagram. And I'll leave most of these things defaults. And I'm going to call this the same thing as my workspace name and my design name. So I'm going to call it Tuesday. And then we specify inputs and outputs. So let's make an input A, and it's going to be 2 bits. So I'm going to make it an array. So if you've done programming in C, right, you know arrays in C start from index 0. Same thing in Verilog. Okay, so A is going to be a collection of 2 bits, and those bits are going to be A bracket 1 and A bracket 0. Alright, so then I'm going to say new, and I'm going to specify another input B, and that's also going to be an array that's 2 bits, B1 and B0. And then I'm going to specify an output, which I'm going to call sum. I'll label that as an output. And that's going to be 3 bits. Sum bracket 2, bracket 1, and bracket 0. And this is a system diagram for a 2-bit adder. A is a 2-bit number, B is a 2-bit number. This is going to add them together and produce a sum, which is a 3-bit number. Alright, so we get 38 lines of Verilog for free. And this is all comments. Okay, we can do whatever we want with those. This is where our Verilog module actually begins. It's named Tuesday. Oh, there we go. I was waiting for that. I'm dead. Well, dang. So the program crashes for me because I'm not on a Windows machine and I'm using a Windows emulator, and Windows emulators are usually kind of funny, especially with newer software. This program has never crashed on me when I use it from Windows, and so hopefully it's not crashing on other people either. If it is, definitely let me know, but this is just a problem with the Windows emulator I'm using because it's, you know, a free emulator. This was the one reason that I used to use Windows at all, and normally, you know, I would take my my Clark laptop, which is Windows, and I would use that for this piece of the course. Well, my Clark laptop is locked in my office, and I haven't been able to get there to get it out of quarantine. So this emulator was working well, and I think it works if you're willing to restart it periodically. But let's see what we can do. Nope, that's going to do it. Alright, so we're going to do our 5-minute break right now, and I'm going to get this back to where it was. We'll come back at about 12:50, and let's finish writing this and simulating it, and then we'll talk about Verilog. Alright, let's take about a 5-minute break. I'll be back after that. Alright, so I'm back. Yeah, so I did get it to work. I'm starting to learn its quirks, but I could go under File, Recent Files, Recent Workspaces, and I can open Tuesday from there, and that brings it back up to where it was. And it feels like if I do too much clicking around up here, it tends to crash, which makes no sense, but these things become superstitions sometimes. But anyway, I will save my work frequently and proceed. And by the way, it's worth mentioning. So this is a free student edition of the Aldec tool. The actual commercial editions can cost a ridiculous amount of money, right? Hundreds of thousands of dollars to get a license for the full commercial version. And sometimes the commercial versions crash just as much as this, right? These programs are phenomenally complex. They can do a lot of sophisticated optimization and analysis on very large designs. When I was a grad student and I was taking a course on that involved Verilog, right? I had a design and I would run the tool, and the tool was running for about 30 some hours. And after 30 hours, it would say, you know, internal error detected. Please send the following log report to the manufacturer, right? And it gave me a location of a file they wanted me to send to them to help them debug their software. That was after like 30 some hours of having this thing try to compile my design. And this is not uncommon, right? Now, Usually it's not going to crash as often as you're seeing here. Like I say, I'm using a Windows emulator, and that's kind of inherently error prone. But sometimes you have to deal with buggy software. It's kind of a reality. And especially in this field where you're working with Verilog, and you may be working with software that comes from a particular chip manufacturer, that may be the only software choice that you have. And when you have software that's only available from one place, it's often going to be buggier than software where there's competition, right? Because, this is why open source stuff works so well. Because, it's crowdsourced. Lots of people looking at the code, lots of people working on bug fixes, and so on. So sometimes things will break. And, for the rest of this course, I'm just going to kind of deal with this and see if I can figure out how to make it break less. But I'll save my work frequently, and worst case I can always start over with a new module. Hopefully none of this is an issue for you working under a Windows system though. Alright, so let's write some code. We've got the module name. We've got 3 connection points, A, B, and sum. A is a 2-bit input, B is a 2-bit input, sum is a 3-bit output. And we don't have to worry about this word wire yet. It's saying that basically these things don't have any memory. We're going to connect them to circuitry, and that's what's going to drive their voltage levels. So enter your statements here. I'm going to say assign sum equals A plus B. And that's it. Just that one statement. And I'm going to say compile. And it says 0 errors, 0 warnings, analysis time 0 seconds. Okay, that's the one that might say 30 hours someday. Alright, what I've designed is I've written Verilog code for a module that does 2-bit addition. This plus sign means adding in the arithmetic sense. If I want to do a Boolean operation like an OR, we use this symbol. Okay, when we do a plus sign in Verilog, that means addition. Just good old adding 2 things together. So I've said take A and B, these 2-bit numbers, add them together, and then connect the output of that addition to this set of wires called sum. So let's simulate this now. So simulation steps: File, New, Waveform. And then simulation, initialize simulation. And it'll say select the top level design unit. This is like naming your main program. How do you simulate the AND Boolean expression? That should be an ampersand. So that should give you an AND. And these are the same things you use in C and Java and other languages. Alright, so select the top level design unit. We're basically naming like the main program, right? So I'm going to say Tuesday, our module named Tuesday. Let's apply that and say OK. And now I've got a window. This is going to show my waveforms over here. Here's the connection points to my module, and I'm just going to drag these into here. So I'm going to drag A and B and sum. And there's a little plus sign next to these. If I click on that, I can see A is 2 bits, A bracket 1 and A bracket 0. Alright, so let's add some stimulators so that we can drive this simulation. So I'm going to right click on A, and I'm going to go down to where it says stimulators, and I'm going to put in a value. Well, let's make a counter. Okay, so we're going to count up. We're going to start from 0. We're going to count up by ones, and we're going to count let's count every 10 nanoseconds. Okay. So that's going to be my input for A. Now I'm going to click on B and say stimulators. And B is also going to be a counter. But, so A is 2 bits. So A is going to go through the following values. Right, it's going to loop through these. And I'm saying that each of these is going to be 10 nanoseconds. Which means to go through all 4 values is going to take 40 nanoseconds. So I'm going to make another input B, and I'm going to count slower. Every 40 nanoseconds, I'm going to increment B. Right, so I'm going to say B is a 40 nanosecond clock. And what I'm trying to do is test my circuit, so I want to give it different combinations of A and B. So B, I'm going to say, is a counter that's going to count every 40 nanoseconds. It's going to count up, starting at 0, modified by 1. So I'll apply that and close. And now I'm going to hit this button which says let's run for 100 nanoseconds. And let's see what that does. Well, it's showing me in decimal. Right here I'm seeing a 0, that's the value of A. This whole section over here I'm seeing a 0, that's the value of B, and it's telling me the sum right here is 0. And if I click, anywhere here, I can see the values of A, B, and sum. This is telling me 0 plus 0 is 0. If I click over here, right, A is a 1, B is still a 0, the sum is 1. 1 plus 0 is 1. If I click over here, A is a 1 and B is a 1, right? A is 1, B is 1, 1 plus 1 is 2, that's the sum. Right? 2 plus 1 is 3. And let's run it another 100 nanoseconds, right? And let's come over here. Let's do the ultimate test right here. 2 plus 2 is 4. So this is a functioning AND gate, functioning adder, right? And over here is 3 plus 0 is 3. Let's run it a few more times. And we should be able to find 3 plus 3. Right here, 3 plus 3 is equal to 6. And I can expand these inputs, and I can expand the output and see, the actual individual bit values. So here A0 is a 0, A1 is a 0. Right? Over here, A0 is a 0, A1 is a 1. Right? So A is the binary value 1, 0. Right? So this is A bracket 1. This is A bracket 0. And if we want to add 3 to that, then we want to set B equal to 1, 1, where this is B bracket 1 and B bracket 0. And there should be a spot on our timing diagram where that's the case. Right here. A1 is a 1. That's this trace right here. The trace below it is A0. That's a 0. And then my B inputs, B1, that's this line right here, is a 1. Sorry, B1 is a... Alright, so let's look right here. A1 is a 1. That's this upper trace right here. A0 is a 0. That's this lower trace right here. That's our 1, 0 going in for A. If we look at B, right, B bracket 1, that's this upper trace right here. That's a 1. And below it is B bracket 0. That's this upper trace. That's also a 1. So our B is equal to 1, 1, right, which is the number 3. And if we add those together, we should get a 5. While our sum, the most significant bit, sum bracket 2, is a 1. And sum bracket 1 is a 0. And sum bracket 0 is a 1. So our sum from most significant bit to least is 1, 0, 1. Right, where this is sum bracket 2. This is sum 1. And this is sum 0. Right? And this is showing 2 plus 3 equals 5. So this is a 2-bit binary adder. Right? This is lab 4. But it was done with, you know, literally one line of Verilog code. And if I wanted to make a subtractor, that's all I got to do. And I can recompile. And if I restart my simulation, let me collapse these again. Right? So 1 minus 2 is what? Well, it says it's equal to 7. Well, does that make sense? So our sum is 3 bits. Okay, so we've got 3-bit numbers. And we're trying to calculate 1 minus 2. Well, 1 equals this. 2 is equal to this. So if we complement all the bits and we add 1, this is what negative 2 looks like. And if we add those together, 1 minus 2 equals 1, 1, 1. Well, why is 1 minus 2 equal to 7? Because if we look at this number as a 3-bit 2's complement number, this tells us this is a negative number. What is it the negative of? Complement all the bits, add 1. And we get the number 1, so this is equal to negative 1. So 1 minus 2 equals negative 1. That's what that trace right there is telling us. So this is a subtractor. It's using 2's complement, it's using bit-by-bit addition, it's doing all the stuff that we've been doing this whole course, right? But we built a circuit to do this with one line of Errorlog code. Assign sum equals a minus b. Okay, this is why Verilog is the way that Silicon is done today, right? We don't use protoboards, we don't use K-maps, we write Verilog code. And with a few lines of code, you can describe a circuit that does all kinds of amazing things. You can describe circuits that you know, display on a TV set or a computer monitor. You can do things that do encryption and so on and so forth. Okay, it's a really powerful way to design circuitry, and it's a whole lot faster than what we've been doing up to this point in the course. So, incidentally, for your homework assignments, right? Let's take a quick look at those, because you'll be using this tool. I want to show you how to capture stuff. So homework for 7, for example, write Verilog code to implement a 3-bit binary to 8-line decoder. Write Verilog code to implement an 8-line to 3-bit encoder, right? So you're going to be writing Verilog code. So in addition to the code, include design documentation either as comments in the code or separate document. We'll talk about that. But basically what you're going to turn in for here is Verilog code, right? So for example, write Verilog code that outputs, here's the code. Okay, so you're going to turn in all of this stuff. Okay, but I also want you to turn in the simulation. So, you know, step through your simulation, shrink it down if you have to so that it fits, right? And then take a screenshot, right? Or whatever you're using to capture. and go in and, you know, crop that. So turn on your cropping tool and, you know, set this down like that. And crop it. Now I've got a nice picture that I can put into my homework assignment, right? And I can put the Verilog code on top of that or below it, and I can put, you know, I can write in what this was and so on and so forth, okay? And the same thing for the lab. So again, you know, my suggestion from week 1, get comfortable with your tool set, right? Get good at doing things like screen copies and saving and cropping and rotating and stuff like that, right? You'll be doing it the rest of your lives. So keep building up a toolkit that works for you.
Do you want the Verilog code in text, or do you want it like a photo?
It's probably easier to put it in as text. If you do a photo, just make absolutely sure that it's completely legible. But it's too tempting for people to just grab a photo with their camera and it's fuzzy and hard to read. But depending on your text editor, sometimes, you know, you copy this and it's all nicely formatted, and then you paste it and it comes out, you know, all pushed to the left. Yeah, use the snipping tool. Snipping tool is great for Windows.
That's what I meant by photo, is like a screenshot.
Yeah, as long as it's legible. If there's any question about it, right, you can just copy this text and then, you know, go into whatever your favorite word editor is. And paste it, right? But sometimes it destroys your indenting. I didn't have a lot of indenting in here. And my suggestion, if you're going to put this in as text, pick a font that's proportional spaced like Courier, or something equivalent to Courier. So that things like, you know, if you have things where you're trying to line up stuff, right, like making all of your dash lines end together, you need a proportional spaced font for that if you use, or a fixed space font for that. So play around with the tools, right, and as long as I can read clearly what you've written, I'm happy. Alright, other questions on that? So I guess let's talk about the homework and the lab, and then we'll go into Verilog. But there's a thing that's been posted on Canvas for a while, this introduction to Verilog, which is really all I'm going to talk about next. But you can certainly read through this on your own. And this is something I put together a few years ago, well, a number of years ago, and then I updated it in 2018. But this is just kind of a quick run through of Verilog. So, you know, the stuff we've been doing where we basically make a module and we use an assignment statement to build a simple logic block. But what we want to start talking about next is this idea of behavioral Verilog, right? For example, this addition program that we just did, where we said, you know, take two-bit numbers, add them together, and get a 3-bit sum. Okay, so we'll keep going through this in a few minutes, or Thursday. But let me talk about the homework. Let's look at the homework in the lab. So write Verilog code to implement the function f of abc equals a bar b c bar, or a bar b bar c, or a b bar. Okay, it's just an arbitrary function. It's a warm-up to using Verilog. So the solved version, right, is a different function, a bar b c or abc. But you can see, you know, you do ands with an ampersand, you do ors with a pipe, and you do nots by putting a tilde in front of something. You can do parentheses to group things, to say I want to be not a anded with b, as opposed to, you know, a NAND of a with b. And it's an assign statement. So assign output equals whatever expression you want to calculate. So this one, pretty straightforward variation on this one. In the other homeworks, you know, I've said don't look at the solved problem and try to modulate it. With programming languages like Verilog actually a pretty good way to learn Verilog is to look at Verilog code. Okay, so don't just blindly try to replace this with this, right? But you can look at this and you can think about, what is it doing? Why does this say input wire A? What if I change that to output? What if I don't say wire, right? You can experiment with this as you work towards a solution to this problem. Okay. Question 2, we're looking at implementing a circuit with memory, right? A latch. And we haven't talked about the always block yet. The always block is key to building things that are stateful, things that remember information from the past. But this is basically saying, right, here's a module. It has an input called a clock, has a D input, it has a Q output. And we have one line of code which says when the clock changes from low to high, the positive edge of the clock, okay, positive going edge means when you change from 0 to 1. That's the positive edge. When you change from 1 to 0, that's the negative edge. So in Verilog, we can say at the positive edge of the clock, let's set Q equal to D. Okay, and we have to talk about details of that. But for question 2, you're going to do the same thing, but you're going to make a T latch instead of a D latch. Question 3, you're going to make a positive edge triggered SR flip-flop. Question 4, you want to make a 4-bit binary counter that counts down. Question 5, you're going to make your decoder. So take in a 3-bit number and choose one of 8 output lines to set high. Right, so 3 select lines, 8 outputs, Y0, Y1, Y2, down to Y7. And you want to set one of these high based on the value of your select lines. So if you set your select lines to 1, 0, 1, Y5 should be high, everything else should be low. Okay, that's what this means when it says a 3-bit binary to 8-line decoder active high. If it said active low, you would want your selected line to go low, everything else would be high. Okay, question 6, Verilog code to implement an 8-line to 3-bit binary encoder. I don't know if we've talked about binary encoders. Yeah, we'll come back to that one. Question 7 is your 3-way intersection with red, yellow, and green lights. This will not be a question that I grade, but I will definitely look at it. Okay, but this is your lab 6 circuit in Verilog. Okay, and you could do this by, you know, writing the circuit that you came up with for lab 6 in Verilog, but that's not the best way to do it. Right, so this is a chance to kind of take a step back and rethink lab 6 in terms of state machines. And if we try to do that, if you just start making a state table and you think of, you know, 3 lights and 3 lights and 3 lights, and that's 9 variables right there, and you've got 3 car sensors and so on, you get a really big table. Okay, but here's a hint for that problem. Here's a way to think about this in terms of states. At any given moment, there's a lane that has priority, right? Assuming you don't have a state where all the lights are red, because that's just kind of mean. So, you know, go back to lab 3 where we had just green and red lights. One of these would be green, the other 2 would be red. Okay, so that system had 3 states. When we put yellow lights in, we've really only got 6 possible states. And I can call these states the following. I could say west is green, or south is green, or east is green, not Q, green. Or we have yellow lights. West could be yellow, south could be yellow, east could be yellow. And these 6 states describe every possible situation for this traffic light. Right? I haven't mentioned red, but you know, if we're in a case where this is red and this is red and this is green, that's my green east state right here. If this is turning yellow, right, that's my east yellow state. If east is red and south is turning yellow, because it was green, that's my south yellow state. So there's really only 6 states for this intersection. And we have 3 sensors, which I can think of as, you know, west, south, and east. And so what does the state diagram look like? Well, if our west light is green, and a car comes from the south, then we want to go to west yellow. And in fact, if a car comes from the east, we want to go to west yellow. Right? So you can build this up from this idea of 6 states. And you got to think about what your inputs are. So we have 3 inputs. And so if we had, you know, state, and our input was like west, south, east. Well, we've got 8 arrows coming from each state because there's 8 possible combinations of this, but we can adopt some shorthands, right? Or not. So if there's a car on the east, we're going to go to west yellow. And it doesn't really matter if there's a car on the west or the south. And if there's a car on the south, we're going to go to west yellow. It doesn't matter if there's a car to the east or the west. And if there's no cars to the south or the east, doesn't matter if there's a car to the west, we're going to stay in the west green state. So there's the whole set of transitions from west green, and the only place we can go from west green is to west yellow. But from west yellow, you know, we could go to east green, or we could go to south green, depending on what the car situation was that took us from west green to west yellow. So play around with that, right? Big sheet of paper or a good whiteboard with a good eraser or something that you can design and redesign. But it's a good exercise to think about how you describe these transitions from one state to another. Okay, totally different from how I suggested doing Lab 6 when you were actually building it in Tinkercad with the delayed old green signal and comparing that to the original undelayed old green and so on and so forth. Right? This is the state machine approach. And you'll end up with a circuit that you wouldn't want to build in Tinkercad, right? Because 6 states, that's 3 flip-flops and 3 inputs. It's a lot of circuitry. But in Verilog, not too bad to describe. Alright, so that's question 7. Question 8 is looking at an ALU. So we need to go back and talk about ALUs in more detail. But basically, you know, we know how to do addition. And if we know how to do addition, we can do subtraction if we can generate a 2's complement. So here's a system diagram for something called an ALU. So it takes a number A, which is 8 bits instead of just 2. It takes a number B, which is 8 bits. And it produces an output, which I'll call X. And I'm going to make this output 16 bits. And it says an ALU, that's an arithmetic logic unit, which adds, subtracts, and multiplies 8-bit numbers. Well, if it can add, subtract, and multiply, how do we tell it which to do? We have an input that we think of as a function. So I'm going to have a function 1 and a function 0 bit. And I'll make a table describing what this does. So I'm going to say if F1 and F0 are both 0, the output is A plus B. If F1 and F0 are 0, 1, the output is A minus B. And if F1 and F0 are 1, 0, the output is A times B. And if F1 and F0 are both 1, I don't know, maybe it's a don't care. Maybe I'll do something different. Maybe I'll just set the output to 0. But this describes, how I want this circuit to act. And now this one piece of logic, I can say, hey, add two numbers for me. Just put these both to ground. My numbers get added. The sum comes out here. Now I say, please multiply these numbers for me. Well, connect this one to a logic 1, leave this at logic 0. Now this is the product of A and B. Okay, in ALUs, you find these inside computers, right? These are the parts of computers that do the arithmetic operations, addition, subtraction, multiplication, division, all that other stuff. Okay, so think about how you would design one of these in Verilog. In Verilog, we can add, subtract, we can multiply with a star. So it's really just writing the Verilog to specify what operations you want performed. Okay, again, for each of these, I want to see the Verilog code and then try to implement it and do a simulation. Alright, now let's take a look at the last lab. So the last lab, again, you're not using Tinkercad, you're using this Aldec HDL tool, okay, the student edition. So preparation, go ahead and download, do that one-time setup. Hopefully that's done. And then 4 experiments. So experiment 1, create a simulation waveform for an 8-bit even parity checker with Verilog. System accepts an 8-bit data and outputs 1 if there's an even number of 1s, otherwise it outputs 0. So what does this mean? Let me show you a 3-bit even parity. So we bring in 3 bits and we generate an output which I'll call X. Okay. Even parity number. Output of 1 if there are an even number of 1s in your input. Otherwise, output is 0. So output of 1 if there's an even number of 1s in your input. All right, are there an even number of 1s? Well, no, there's not here, so that's a 0. But here we do have 2 1s, that's an even number, that's a 1. There's 2 1s, there's only 1 1, that's an odd number of 1s, so the output is 0. There's an even number of 1s, there's an odd number of 1s, odd number of 1s. How many 1s do we have in this first row? 0. Okay, and 0 is an even number. It's divisible by 2, it's 2 times 0. So this has an even number of 1s. So that's a 1. If you make a K-map for this, you get your checkerboard. Okay, your checkerboard tells you think about XORs, think about XNORs. That's the hint in here. XOR is helpful. So to do this for 8 bits, right, don't make a truth table with 8 bits. That's got 256 rows in it, okay? But think about this think about how you would use an XOR or an XNOR circuit to do this function, and then think about, suppose I had 4 bits, B0, 1, 2, and 3, how would my circuit change? And then see if you can go from there to 8 bits. Okay, and we're not, building the circuit like this. We can do this with Verilog. So think about that. There's a number of ways to do this. One is using XORs. There's other ways also. Okay, so that's your first experiment. For the lab, I definitely want to see, source code. I want to see simulated output, and I want you to talk about this, right, as in a lab report. So experiment 1, we're creating an 8-bit even parity generator, right? And then tell me what you're doing. Tell me what the theory is. Tell me how you're coming up with a design, and then show me the Verilog code, and then show me the simulation of it using this student edition software. Okay, then go on to experiment 2. Waveform for an 8-bit up-down synchronous binary counter using Verilog. Okay, what's an up-down counter? Well, it has an extra input besides the clock, which says, do I want to count up or do I want to count down? So you've got a clock going in. Got a signal, I'll just call it up, and here's my 8-bit output. And up equals 1, count up on each clock tick. Up equals 0, count down on each clock tick. Right? This is like the ALU. It's building a circuit that does multiple things, and you have to have a way to tell it what to do. In this case, we put a signal in here to say, should you count up or count down? Alright, experiment 3, design and create a simulation waveform for a 16-bit shift register. Circuit will accept input on the rising edge of the clock and output the input value after 16 full clock cycles. This is your delay circuit again. This is what you did in experiment 1 for lab 6. That was a 2-bit shift register. You had a pair of flip-flops. You had an input, you had an output. You had these things clocked together. And each time you clock, the input value goes into here. The value that was in here goes into there. Well, if you extend this to, say, 4 flip-flops, right? The first time you tick, your value here, which we'll call A, gets loaded into this flip-flop. The second clock tick, let's say you have a value B, A gets copied into here, B gets loaded into here. The third tick, let's say your input is C, A is going to get copied into here, B is going to get copied into here, and your input C is going to go into here. And your fourth input D on the fourth clock tick, A is going to shift over to this last stage, B is going to shift into here, C is going to shift into here, and D is going to get loaded into here. So each time the clock ticks, the contents of the shift register are moving over 1 bit. And if you set your input to A, after 1 clock tick it's here, 2, 3, 4 clock ticks it ends up in here, and you see it appear on the output. It's a longer delay circuit. It takes 4 clock ticks instead of 2. And if you look at each of these outputs in a timing diagram, it's really obvious what's going on, because you'll see a nice staggered staircase. If you take your input and you raise it from a 0 to a 1, your flip-flop inputs will go from this to this to this to this to this. And if you plot this as a timing diagram, you'll see something to this effect. Alright, so you're going to do that, but you're going to use 16 flip-flops. So that after 16 cycles, the original input appears on the output. And then that gets used in your fourth and final experiment, which is making a circuit that detects when a certain event has occurred a certain number of times. So design and create a simulation waveform for a 5 out of 16 event detector. So here's the idea. You have a clock. You have an input which can be 0 or high. And at each moment, the system should say, have I seen exactly 5 inputs that were equal to 1 on the clock ticks? So through all of this, the number of ones that the system has seen is 0. On this clock tick, it's seen 1, input of 1. Here it's seen 2, here it's seen 3. Here it's still seen only 3 1 inputs, only 3 1 inputs. On this clock tick, it's seen 4 now, right here, 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 and here. And then on this clock tick, it's seen 5. Right there, 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 and there. At this clock tick, since it's now seen 5 inputs out of the last 16 clock ticks, the output goes high. And on the next clock tick, guess what? It's seen 6 inputs. 1, 2, 3, 4, 5, 6 inputs that were high. So it's not seen 5 out of 16, it's seeing 6 out of 16, so the output goes low again. Okay, so this is going to involve using a shift register because you need to remember the last 16 values that you sampled. And how do you know if exactly 5 of those were equal to 1? Well, here's a big hint. Just add together those 16-bit values. And if the sum is equal to 5, then you know exactly 5 of them were 1s and all the others were 0s. Okay, that will save you from writing 65,000 if statements. So it's a good hint. So add together the 16 bits that you have in your shift register. If the sum of those bits is exactly 5, then you know you've got 5 1s in your shift register, which means 5 out of the last 16 clock inputs were these input equal 1 events, and that's when you set your output high. Okay, so this will make more sense as we talk about Verilog always blocks, which we're going into right now. And then the usual boilerplate requirements for the lab. But again, for the lab, make sure you have Verilog code and you have simulation output. Okay, design and simulation waveform. Any questions on that? All right, so let's dig more into Verilog. So here's the Verilog intro that you can download from Canvas. And so we've done the basic setup a few times now, right? It's module, the name of the module, parentheses, list of the ports, semicolon at the end. And then mostly we say whether these ports are inputs or outputs, and we're always saying wire. And then we have assignment statements, assign sum equals A plus B or A minus B, for example. And we talked a little about comments and case sensitivity and so on and so forth. So combinational circuits, that's what the assign statement is doing for us. Take A, B, and C, put them together to the inputs of an AND gate, take the output, connect that to X. There's a 3-input AND gate. You can put this inside your Verilog code and compile it and simulate it, and you'll get a nice AND gate simulation. The output will be low unless A, B, and C are all 1, and then the output's high. Okay, we talked about the ternary operator, so you can do things like this with this syntax. So this is something you do in C, this is something that you do in Java, and so on. So if select's equal to 1, this says assign out equal to in 1, otherwise set it equal to in 0. Okay, we talked a little about instantiating one module inside another, but we're not going to do a lot of that. So let me go on to behavioral Verilog. Okay. And we already did the addition example. Okay. So let's look at event-based stuff. And pretty much everything we do here is going to involve designs that have a clock input. Okay, really any modern circuit design that we do anymore, there's a clock input, right? Why? Because that's what drives the flip-flops to respond to the changes in their inputs. So most of the modules we make, at least one of the inputs is going to be a clock. Okay, so this is an example I call a clocked comparator. It looks like this. Let me see, how many bits am I using? I'm just using 1 bit. So here's what this looks like. This is a circuit that will tell me if A and B are equal to each other. So right here my circuit should output a 1, same here, but here it should output a 0. Okay, well that's not too bad to build, that's just an exclusive NOR gate. But remember, when we're dealing with circuits, right, there's glitches. Values can change to intermediate values while circuitry is processing changes to inputs. There's propagation delays. And A may be on its way to becoming a 1, and B may be on its way to becoming a 0. But in that process, depending on when these things change, we might get to temporary states where A and B look the same. So what we're doing is we're making a comparator that only looks at the inputs when a clock ticks. So I can set A and B to be the same, I can set them to be different. That's not going to affect X until the clock ticks. And at the moment that the clock ticks, I want this circuit to look at A and B, and if they're equal, set the output to 1, otherwise set the output to 0. Okay, this is not a straight combinational circuit, because this is not strictly how it performs, right? If the clock is stable, it doesn't matter what A and B are, X is not going to change. So it's going to look at the inputs when the clock ticks. Okay, it's a pretty useful circuit actually. So here's how we could write this in Verilog. I can say always at the positive edge of the clock, begin. So begin, end basically brackets a set of statements that go inside this always block. Okay, and what do I say? If A is equal to B, set X equal to 1, otherwise set X equal to 0. Okay, it's a really straightforward description of exactly what I just said with this picture. Right? When the clock ticks, if A is equal to B, set the output equal to 1. Otherwise, set the output equal to 0. Now the syntax is goofy because it's Verilog, and Verilog has goofy syntax. But if you read along with me, right, it says at the positive edge of the clock, that's when the clock ticks, do the following statements. If A is equal to B, set X equal to 1. Otherwise, set X equal to 0. Alright, so ignoring the syntax, right, that's the spirit of what this code says. At the positive edge of the clock, do the following. If A is equal to B, set X equal to 1, otherwise set X equal to 0. Okay, now for the syntax, right? 2 things that pop out. One, we have the statement reg X. And normally we've been making things wires, but if we say reg X, that means I want a flip-flop. I want to be able to remember a value for X. Because we're not going to say assign. When we say assign, what we're doing is we're connecting this port S to the output of some circuitry, in this case circuitry that does 2-bit addition. Is that a question? So reg X says I want to remember a value for X. Okay? Because we're not going to assign X equals 1, because if we said assign X equal 1, that would connect X to 5 volts. And if we said assign X equals 0, that would connect X to ground. Yeah, somebody's mic is on. I'm not sure if it's a question or if it just got turned on inadvertently. But the voice is breaking up, so if there's a question, go ahead and send me a message in chat, and then we'll get your mic working. All right, so assign x equals 0 is a bad thing. It connects x to ground, and that's it. X is always going to be a 0. And to say, you know, if a equals b, oh, that's cool. To say if a equals b, connect x to 5 volts, otherwise connect x to ground. Well, we can't change the connection of x to either 5 volts or ground. Okay, we were asking this thing to rewire itself, which we don't generally do. So instead, we're saying x is a flip-flop. Okay, it's a register. And when the clock ticks, this positive edge of the clock, let's load a value into that flip-flop. Let's load a 1 if a equals b. Let's load a 0 otherwise. So this is actually going to synthesize to a circuit like this. Something like a D flip-flop. Here's our clock, which comes from outside the circuit. And then on the positive edge of the clock, set x equal to 1 or 0 based on whether a equals b. So we're going to have a and b, and those are going to go through an exclusive NOR. And that's going to go into the D input. And then the Q output, that's going to go to x. And so this is the module that our circuit's probably going to come out to be from that Verilog code. Right? And we didn't say that. We never mentioned, you know, make a D flip-flop and all that kind of stuff. We said at the positive edge of the clock, if a equals b, set x equal to 1, otherwise set x equal to 0. The software, which has already taken the Engineering 250 course, knows how to do this. It knows that I can build an exclusive NOR that will output a 1 if a and b are the same value. And it knows that if I feed that to the D input of a flip-flop, and I connect the clock to the clock line, that when the clock ticks from 0 to high, if a and b are equal, a 1 will get loaded in here, x will become a 1. And if a and b are different from each other, a 0 will get loaded in here, and x will be a 0. And once that happens, once the clock has ticked high, if a and b change, it makes no difference because the D input might change, but the Q output won't change until the next clock tick. So a really, really useful thing to do while you're playing with Verilog is think about what you're synthesizing. Think about the circuit that you're trying to describe, because remember, Verilog is not a programming language. It's not a set of steps that we want to perform. It's a description of a piece of hardware, a circuit. So as you're writing code like this, which looks like, you know, C code with an if-then statement, think about how this turns into hardware. And sometimes you'll write Verilog and you'll try to compile it and it'll say this can't be synthesized. And it means you've described a circuit that's physically impossible to build. Okay, that's a good point to step back and think about, what does this circuit describe, right? And this is quirky. This takes more than a couple of weeks to get used to, okay? But we only have a couple of weeks. So I want you to stick with it. I want you to do the best you can. I want you to come to office hours and show me what Verilog you're coming up with, and we'll talk about it. And, you know, look at what it's saying and look at ways that we could say something different, okay? It's a process that takes work. But once you get past some magic point in the learning curve, it starts to get really, really easy and intuitive and super fun. And you can come up with some fabulous circuits. And I'll show you some stuff on Thursday that people have posted, you know, open source Verilog code that you can get and you can modify and use. All right, so we'll talk more about these always blocks on Thursday. Keep working on your stuff. Bring questions next time. Come to office hours if you have questions, and I will see you when I see you. All right, thank you.
Have a good day.
Thanks, you too.